Friends, most welcome in the chemistry class. And the chapter solid state is going on. Already we have discussed and you have learned the structure of simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell. For the simple cubic unit cell, that is contribution for one particle for one unit cell 1 by 8. The 1 by 8 corner atoms, simple cubic unit cell, one body atom, that is the contribution of the constituent particle at the body, 100% for the unit cell, and this is the face-centered cubic unit cell. Constituent particle contribution for one face equal to half. So there are total 6 faces. So you know that in the face-centered cubic lattice cell, the total number of atoms, that students, total number of atoms for the simple cubic cell equal to 1, face-centered cubic cell equal to 4, and body-centered, that is 2. We have already discussed this. But students, we have already also discussed number of atoms per unit cell, that is 1 for the simple cubic cell, face-centered 4, and body-centered 2. My dear children, now I am going to discuss packing fraction for the unit cell. And packing fraction for the unit cell, that is the formula. Suppose it is body-centered cubic unit cell. What is the formula of the packing fraction? One is packing fraction, another is packing efficiency. Packing fraction, total number of atoms present in the body-centered cubic unit cell equal to 2, we have proved. So formula is total volume of the atoms in the unit cell divided by volume of the unit cell. So in case of body-centered, my dear children, number of atoms 2. And we consider the constituent particle shape is sphere. So everybody knows the volume of the sphere 4 by 3 pi r cube. So what is the volume of the two atoms? 2 into 4 by 3 pi r cube. So 2 into 4 by 3 pi. And you know the relation of r and a for the body-centered cube. That is root 3 a by 4. This is r equal to root 3 into a by 4. This is the relation of the a and r for the body-centered cube. By putting the value of r here, so we get 0.6802. This is the packing fraction. What is the packing efficiency? This into 100, so near about 68.2%. This is the packing fraction of the body-centered cubic structure. Now face-centered cubic structure, what is the packing fraction? You know that students, number of total atoms present in face-centered equal to 4. So 4 into 4 by 3 pi r cube divided by total volume of the unit cell, and volume of the unit cell in this case, you know that a equal to 2 into root 2 into r. So a cube means 2 root 2 r cube into 100. So 74%. And for the simple cubic unit cell, student, I have given the task to you to complete simple cubic unit cell. The packing fraction will be 1 into 4 by 3 pi r cube into 100 divided by a cube, and a equal to 2 into r. This is for the simple cubic unit cell, and here you will see the percentage of the packing fraction, that is packing efficiency 52.4%. We have already discussed. Packing fraction of HCP unit cell. HCP unit cell means that is pi by 3 root 2. Pi by 3 root 2. Now students, I am going to discuss the imperfections in the solid. What is the meaning of imperfection in the solid? It means when the arrangement of the constituent particles, there arises any kind of defect, then it is known as the imperfection. That is defect in the solid. My dear children, two types of defect. One is the point defect, another is the line defect. But in your syllabus, we have to know about the point defect. What is the meaning of point defect? We should know first. Point defect are the irregularities or deviation from ideal arrangement around a point or an atom in the crystalline substance. Again I am telling what is point defect. Point defect is the irregularities or deviation from ideal arrangement around a point or an atom in the crystalline substance, that is known as the point defect. And line defect means the irregularities or deviation from ideal arrangement in entire rows. This is row, one row, two rows, three rows, entire rows. There is the deviation from the ideal arrangement, that is known as the line defect. But in the syllabus we have to study the point defect, that is the irregularities or deviation from ideal arrangement around a point or an atom. Now, point defect, two types. One is the stoichiometric defect. Point defects we have to discuss stoichiometric defect, impurity defects and non-stoichiometric defect. Stoichiometric defect, impurity defect and non-stoichiometric defect. Now students, stoichiometric defect. What is stoichiometric defect? There are the points defect that do not disturb the stoichiometry of the solid. It means that this defect do not disturb the stoichiometry of the solid. The ratio of the cations and anions remains same as represented by the molecular formula. And this stoichiometric defect also known as the intrinsic or thermodynamic defect. Now, basically these are of two types. One is the vacancy defect, another is the interstitial defect. Vacancy defect, it means that is when some of the lattice sites are vacant, the crystal is said to have vacancy defect. When some of the lattice sites are vacant, suppose here this is the vacant place, because there is no ions is present here. So this is the examples of the vacancy defect. When any lattice site is vacant, then the crystal is said to have the vacancy defect. What does it result? This result the decrease in the density of the substance, because one ions is missing here, so density will be decreased. D for density, D for decrease. It is because mass decrease but volume remains the same. Volume remains the same but mass becomes decreased. This defect can also develop when a substance is heated. So vacancy defect created when the solid substance is heated. So what is decreasing here? Density is decreasing here. When this vacancy is created? When the substance is heated. So this is the basic things. Next is the interstitial site. Suppose you have seen that is A plus ion. It occupies the interstitial sites. So when some constituent particles also occupy an interstitial site, then the crystal is known as the interstitial defect. This defect increase the density. Because the constituent particles number is increasing. So for the interstitial defects, what is increasing? Density increasing. I for interstitial, I for increasing. So in the interstitial defect, the density is increasing because constituent particles increasing. It is because the mass increases but volume remains the same. Okay. Now students, the cations, a vacancy caused by one ion is accompanied by the vacancy of the oppositely charged ion. These defects are of two types. Students, one thing I am telling you, ionic solid must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, ionic solids show these defects as Frankel defect and Schottky defect. So I am going for the ionic solids. Ionic solids actually shows the Schottky defect and Frankel defect. But vacancy and interstitial defects are explained above can be shown by non-ionic solid. So the vacancy defect and interstitial defect can be shown by non-ionic solids. But actually, ionic solid shows this vacancy defect and interstitial defects as the Frankel defect and the Schottky defect. Okay. Now I am going for the Schottky defect. What is Schottky defect? In an ionic solids of the type A plus B minus. This is the ionic solids where cation is A plus and anion is B minus. Equal number of cations and anions are missing. Here B, A minus, B plus. So B plus and again here A minus. A minus and B plus. So A plus B minus, A plus B minus. So B plus A minus and B plus. So this is the place of B plus ion. So A plus B minus, A plus B minus. So B minus ion place is here. B minus ion A plus, this place is here. And A plus ion place is here. So equal number of cations and anions are missing. And this is known as the Schottky defect. So what is the Schottky defect? When in the solid, equal number of cation and anions are missing, then the solid develops. That is known as the Schottky defect. It is basically a vacancy defect. It is basically a vacancy defect because just students you see that two vacant places are created here. One for the anion and another for the cation. This is the Schottky defect. This is the Schottky defect. Now, effect on density. This type of defect, like simple vacancy defect, Schottky defect also decreases the density of the solids. So one question is coming frequently in the exam, my dear students. What is the effect of Schottky defect in the solid? Your answer will be the density decreases. Density decreases because number of ions are missing. So mass will be decreased, so volume will be decreased. Schottky defect is shown by ionic substances which have high coordination number and in which the cation and anion are of the almost similar size. Another things I am telling about the Schottky defect, when the coordination number of the solid is very high, it is observed by the ionic solids, by the ionic substance, number 1. Number 2, where the coordination number is very high, number 2. Number 3, when the size of the cation and anions are almost same. Examples: sodium chloride, potassium chloride, silver bromide, cesium chloride. This solid substance, we see the defects like this, that is Schottky defect. Second is the Frankel defect. Frankel defect means this defect is shown by ionic solids. Number 1, the smaller cation is dislocated. The cation A plus is dislocated from its normal site to an interstitial site. My dear children, this is the place and this place is known as the interstitial site. So which is delocalized here? A plus, that is cation. You know that size of cation is smaller than anion. So cation dislocated its place and occupy the interstitial sites. Okay, this is number 2 on the topic Frankel defect. So first of all, which type compound, which type solid will show this defect? Answer is ionic solid. Second is cation is dislocated or anion is dislocated. My dear children, answer is cation. Why? Because its size is smaller. Number 3, Frankel defect is shown by ionic substance which have low coordination number. Okay, Schottky defect show by the solids having high coordination number, but Frankel defect show by the solids having the low coordination number, and in which a large difference in size of cation and anion. But here approximately same size of cation and anion, but in this case the cation and anion size there is large difference. Examples: zinc sulfide, AgBr, AgCl, AgI, silver chloride, silver bromide, silver iodide. One thing I am telling you students, AgBr is a compound, is a solid which shows both type of the defect. both type of the defect. Next here discussing here non-stoichiometric defect. Non-stoichiometric defect two types. One is metal excess defect, another is the metal deficiency defect. Non-stoichiometric defect means the defect discussed so far do not disturb the stoichiometry, that is the stoichiometric defect, but the defect where the stoichiometry of the solid is disturbed. Stoichiometry of the solid is disturbed. That is the ratio of cation and anions does not remain same as represented by the molecular formula. So there is the disturb in the stoichiometry. So this is known as the non-stoichiometric defect. And this is metal excess defect and metal deficiency defect. Now students, this is metal excess defect. What is the meaning of metal excess defect? In this defect, a negative ion may be missing from its normal site. Thus the metal ion becomes in excess. So which becomes excess? Metal ion. Metal ion charge is the positive. Because anion is missing here, so metal ions will be excess. Thus the metal ion becomes in excess. The whole cost by the absence of negative ion is occupied the electron to maintain the electrical neutrality. When a sodium chloride crystal is heated in presence of sodium vapor, you know students, some chloride ions leave the lattice and combine with sodium to form what? To form what, students? Yes, the answer is good, to form NaCl. For this reaction, sodium atom lose electron to form sodium ion. The released electron occupy the anion vacancies produced by Cl-. This E- comes from the sodium. The sodium loses one electron and this electron occupy the vacancy of anion, anions. Okay, now the crystal has excess sodium ion. So which ion is excess here? Sodium ion is excess here. So this is the metal excess defect due to anionic vacancies. An extra cation in the interstitial sites. So A plus in the interstitial site and E minus. That is the electron electron is lost by the metal, and this electron is present here and it is the extra cation. And so extra cation in the interstitial site. Now students, I am going to metal deficiency defect. What is metal deficiency defect? This defect occurs when the metal shows variable valencies. The first criteria, which type solids will show the metal deficiency defect? Answer is, this defect occurs when the metal shows variable valencies. Number 1. Number 2. This defect is shown by FeO, that is FeO, ferrous oxide, FeS, ferrous sulfide, etc. 3 Fe2 plus ions are replaced by 2 Fe2 plus ions. The electrical neutrality is maintained, but the solid contains less amount of iron atoms. Same is true for NiO. 3 Ni2 plus ions are replaced by 2 Ni3 plus ions. So Na plus Cl minus. And here cation vacancies. This is the Na plus Cl minus. And impure substance also present here, that is Na plus Cl minus Si2 plus, and this place Na plus is vacant here. Na plus is vacant here. Na plus is vacant here and Si2 plus is present. And metal deficiency defect. So which type solid shows the metal deficiency defect? The metal which has the variable valencies. And which type solids? Name example of the solids. Example FeO, FeS, NiO, etc. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. To maintain the electrical neutrality, that is 3m2 plus equal to 2m3 plus. And students, metal deficiency defect due to missing of cation of a lower valency and another lattice site occupied by cation of higher valencies. So cation is present here Si2 plus is valency 2 and Na plus valency 1. So what I am telling here, metal deficiency defect due to missing of cation of lower valency. So what is the valency of sodium? So plus 1. What is the valency of silicon? That is 2. So lower valency metal is replaced by another lattice sites occupied by cation of higher valencies. Metal excess and metal deficient compound act as semiconductor. Metal excess compound contain free electrons. You have seen that in metal excess compound has the free electron. So here free electron is present. So metal excess compound and metal deficient compound both conduct the electricity. So semiconductor, they act as the semiconductor because by normal electrons present in the metal excess defect, normal electron present and metal deficient compound conduct electricity through positive holes conduction mechanism, positive hole, because here positive charged missing here. So this type compound, this type solids conduct electricity because through the positive holes conduction mechanism. So metal deficiency defect and metal excess defects. Students, so next day we will discuss the question answer of the chapter. Today up to this. Okay. Good day, students.